Okay.
And recording, yes. Okay. So, Maria, you can start.
Yeah, thank you. Thank you for invitation. It's a pleasure to give a talk here, and I'm going to tell you about anisotropic spin generalization of elliptic Ruijsenaars operators. And then we discuss the related spin chains, long-range spin chains. Okay, and is the following. So firstly, I will talk about the scalar Ruijsenaars model, quantum case. A classical case was introduced by Ruijsenaars and Schneider, and then Ruijsenaars in 87 proposed its quantum version. We know it is the set of commutative operators, which we call Ruijsenaars operators, or in trigonometric case, it's Macdonald operators. And Ruijsenaars proved that the commutativity of these operators equals to the set of functional identities. So, and he proved that this some elliptic function, I will tell you later, satisfies these functional identities. And as usual, there are the most general case, elliptic case, and its degenerations, trigonometric and rational. And in trigonometric case, these operators we know as Macdonald operators. Okay. What I want to do is to construct a matrix version of this story. So we construct some matrix valued operators in terms of elliptic quantum elliptic R-matrix. And we prove that the commutativity of these operators equals to the set of R-matrix identities. So it's our recent results with Andrei Zotov. The trigonometric case of this story was done firstly by Uglov in 1995, and then in 18 and 20 by Lammers and Lammers-Pasquier-Serban, where they use the trigonometric R-matrix or UQ-SLN hat R-matrix and construct the corresponding spin chain, long-range spin chain, which they call Q-deformed Haldane-Shastry spin chain. And I will, at the last part of my talk, I will tell you how to construct these spin chains from these commutative matrix valued operators. So it works in elliptic case and in trigonometric also, and I show you how it is connected with a long-range Haldane-Shastry spin chains. So this is my plan, and I start from old story. So quantum Ruijsenaars model, and tell you how Ruijsenaars proved the commutativity of his operators. Firstly, I show you some notations which I will use for elliptic functions. And I will use odd theta function. This is my notation, and this is a function on the torus with periods 1 and tau. So imaginary part of tau more than 0, and this is the formula for odd theta function. In trigonometric case, it goes to just to sine, and in rational it goes to theta. And I will use the function phi with two parameters, z and h. This is the formula from odd theta function. And it also elliptic function on the torus. And it's not double periodic, like, for example, Ruijsenaars function, but it has some periodicity properties. You may see it here. Is the periodicity properties of this Kronecker elliptic function phi. And in trigonometric case, it goes to the sum of cotangencies, and in rational case, it's just 1 over zeta plus 1 over h. So this is my notation, and the main hero is this elliptic Kronecker function. Okay. How these Ruijsenaars operators looks like. My notation is dk for these operators. Here we have the sum over all sets, over all subsets in k elements. So we have I capital is the subset of the set of numbers from 1 to n, and here it means the number of elements is k. And we have a product such that I belongs to I capital and j doesn't. This function phi Kronecker elliptic function, depending on differences of zeta, and the product of shifts. So we have here shifts with indices I small, which belongs to I capital. And what is shift? This pi. Pi is just an additive shift. So if you have some function depending on zeta 1, zeta 2, and zeta n, eta. So this is just an additive shift operator. So this is the definition of Ruijsenaars operator, and some people know them in trigonometric case and as Macdonald operators. So if you make this changing, if you change the variables, so you use these multiplicative variables t, x, and q, when you obtain these operators in Macdonald form. And this is Macdonald form, trigonometric form of these operators. And here we have not the additive, but multiplicative shift. So this guy shifts, so multiply xi by q when you act on function of x's. So this is the definition of Ruijsenaars operators. And these operators commute for elliptic case and as well for trigonometric and rational case. So what was the idea to prove the commutativity? Ruijsenaars proposed two theorems. Firstly, so if we have decay in this form and phi is some function, so we don't know this Kronecker elliptic function. So and you just calculate this commutator decay in dl. So these operators commute if and only if these identities hold. So this is the identities for function phi. Theorem 1 is just, so the proof of theorem 1 is just direct calculation. So you calculate this commutator and these shifts, and you obtain these identities. And theorem 2, that the Kronecker elliptic function phi satisfies these identities as well as its degenerations. Okay. So what was the idea of theorem 2? How to prove that Kronecker elliptic function satisfies these identities? So you need to prove that left-hand side is double periodic and it has no poles. So you just calculate all the residues, prove that it has the left-hand side has no poles, and check the periodic properties. It's if it's double periodic, you decide that it's a constant, and the constant 0 is easy to prove. So it's some basic ideas how to prove the elliptic identities. And Ruijsenaars showed that phi it's almost unique elliptic function which satisfies the identities, so up to some constant and some exponent. So this Kronecker elliptic function is almost unique for solution of these identities functions. So let me give you simple examples. So when you have two particles n equals 2, we have two operators d1 and d2, and it looks very simple. I draw here a picture. It's very simple, but I then generalize them to matrix case, and you see for these graphical notations. So I just put the dot, this red dot, on the line where I have shift. So here I have shift only P1 and here P2. So this is the graphical notation for D1 and this is the graphical notation for D2. And these operators obviously commute because P1, P2 shifts both variables zeta2 and zeta1. And here you may see that all phi's depends on the difference of zetas. So D1 commutes with D2. And the trigonometric, yes, in this multiplicative notation, the Macdonald form of these operators.
Sorry, the sound is disappear. Masha, we cannot hear you. Could you hear us?
She's lost the signal. I don't think it's that I think that the signal is on. She's back.
Yeah, she's here.
You can't share, you can't see my screen, yes?
Yeah.
So, sorry. One moment. Now it's okay, yes?
Yeah, now we can see. It's okay.
Okay. So yes, I explained that D3 commutes with D1 and D2 because D3 shifts all zetas, and in D1 and D2 we have only dependence on differences of zetas. So D3 commutes with D1 and D2, and not obvious that D1 and D2 commutes. And this gives us the first non-trivial identity with n, where n is 3 and k is 1, as a coefficient at P1, P2, P3. So when you commute this D1, D2, you have, for example, some coefficients like P1 squared, but the coefficient equals 0. Look at the coefficient P1, P2, P3. It's not 0. It's the first non-trivial identity. Okay. More notations because I am going to generalize the
Sorry,
matrix.
but we now
So by
cannot hear you properly. Probably, could you please switch your camera off?
Okay. Now it's better.
Probably, yeah. Thank you.
Okay. But you need to say something. You really will not work. Okay. I and J are capital. I is now subsets of set from 1 to n, and this is ing, so their intersection is 0, and I use the following notations. Ij capital in these brackets means that I take the product of all files where I small belongs to I capital and J small belongs to J. And P with capital index I means that I take product of all shifts with indices which belongs to I capital. By I with this C, I denote the complement set. And when I put some minus near this I capital letters, it means that all zeta with indices from I capital are shifted by minus eta, so you can see it here. And when the Ruijsenaars operators can be written in the following form. So dk is the sum over all I and k variables, and here you have I complement with I, so you have the same. And I just remind you the theorem that the commutativity set of identities. This is the identities in our new notations. I will generalize these formulas for matrix case. Okay, this was the scalar story by Ruijsenaars, and we are going to construct some matrix valued operators. And for this, we use the R-matrix. So what is the R-matrix? It's the solution of Young-Baxter equation. So this is the Young-Baxter equation. I think all know this picture. So what does it mean? For example, left-hand side, we have rjk with argument, so xj minus xk. When so here the lines means where time goes. So first we have the intersection rjk, and I put it here, then rik, I put it here, and then rij. And the arguments, the rules for their arguments is the following. So you take the difference of parameters on these lines. Firstly, you take the left, and this is the picture for the right hand side. Yes, so you may think that we take this red line and just move it here, and we obtain this, and nothing changes. Yes, and when we so the R-matrix is the operator and V tensor V, and when we put this indices I plus 1, it means that we take this R in two spaces, I and I plus 1, and the other spaces it's X just as identity operators, and this operator it acts in n tensor copies of V, but not trivial, only in I and I plus 1 tensor copy. So, and the solution of this Young-Baxter equation is called R-matrix. So some simple solution of this equation, for example, identity operator, permutation operator, yes, just permutes two tensor spaces, And for example, linear combination of these solutions, not all, but this linear combination holds the Young-Baxter equation, so a rational Young R-matrix. But we will look at the elliptic solution of this equation, and namely the elliptic Baxter-Belavin R-matrix. So I put it here for GL2 case, but in fact, all the construction works for GLN case, and the definition is can be written even for GLN case, but it's really takes a long time to do it, so I just take for this presentation the GL2 case and elliptic Baxter-Belavin R-matrix, and we know it is 6-vertex R-matrix also. So what is the definition? Here I have sigmas. It's just the Pauli matrices. So this is the notation, and again, phi is the Kronecker elliptic function. This phi with indices 0, 0, 1, 0, it's just Kronecker elliptic function with some special arguments or some shifts, so you may see them here. And here this solution, this elliptic 8-vertex R-matrix in matrix form. Okay. So what are the properties? Firstly, it satisfies quantum Young-Baxter equation, and it also satisfies unitarity property. It means that Rij times Rji, so with these parameters, it's proportional to identity operator with some factor. This factor can be written in terms of Weierstrass elliptic P functions. And if you normalize this R-matrix, so you divide it by elliptic Kronecker function. So I put the bar for this notation. It's normalized R-matrix when R bar Ig and R bar Gi gives just the identity operator. And I draw the picture for this like that. So Rj, Rij, Rji. So here we have Xi line and Xg. And this it's just the straight lines due to the unitarity property. Okay. You can also think about the degeneration of this R-matrix. The trigonometric degeneration is given here, and it's just the 6-vertex R-matrix. And the rational degeneration about I told you about, it's Young rational R-matrix. So it's just identity over H plus permutation over zeta. So all the construction works for the trigonometric and rational case, where you take the corresponding R-matrices, this for trigonometric, this for rational, and phi also corresponding phi, trigonometric degeneration of phi, the sum of cotangents or rational degeneration of phi. So you may think just about some trigonometric or rational case. It's easier. Okay, what are the main statements? Firstly, we introduce some spin operators, some matrix valued operators, and what is the definition? So dk in spin case, we have the same as in Ruijsenaars. So this factor is some product of phi's. This pi is now this pi is rep with this R-matrix. You have R-matrices. It means that we have some product of Rij, and again I small belongs to I capital, J belongs to J. And if we don't have this, how to say it, not bar, prime, yes, prime. Yes, if it's with prime, it means that I more than J, and here it's just I less than J, and in R prime I greater than J. Okay, so but I don't write here the order of these R matrices, but I would like to emphasize that it's really important, the order, because they don't commute, but I will give you the exact notation later. But just now you think that it's product of R matrices. And we formulate the theorems, which are matrix generalization of Ruijsenaars construction. So this dk, these operators, spin operators commute if this R-matrix identity holds. So here are some non-trivial R-matrix identities. And the theorem 2, that the elliptic Baxter-Belavin R-matrix satisfies these identities. So that's why we obtain the elliptic matrix valued set of commutative operators, which we called anisotropic version of spin Ruijsenaars, quantum spin Ruijsenaars operators. Okay, I will give you the precise construction and the notation later, and I would like to start with the examples. So let me show you the example for n equals 3. So what we have? We have these operators, and I draw the picture for them, how I do it. So here I have this item. It means that I shift on the, so this red dot means the shift on the first variable shift. And here it means that I take the set 2, 3 and the set 1. And I take some i's from here and some j's from here, and I obtain the product of phi's. So zeta 2 minus zeta 1 and zeta 3 minus zeta 1. So this is the graphical notation of the first item. Okay, what I do for the second? This means this factor with phi's, this item with phi's. And for this guy, I draw the following picture. So I have R21 firstly. This is this intersection, line 2 with line 1. When I have shift, I put here red dot. And when I have R12, so it's this intersection. So these lines show you how the order of R matrices. Okay, and the last item is this. So the same for phi's. And what we have here, we have R32, it's here, then R31, then dot, which means we put on the third line, and then R13 and R23. So this is the picture. And the sum is the graphical notation for D1. The same I do for D2, but in D2 we have two shifts. So I have two dots here with R matrices. And for this item, I have this picture. And the simple operator is D3. So it's just shifts all zetas. Okay, this is the example. And when you, for example, want to find the commutator, so D1 with D3 and D2 with D3 commute because D3 shifts all the variables. Non-trivial is the commutator of D1 and D2. And for example, you want to calculate it. And let us show, for example, for coefficient P2 squared, P3. How to obtain this coefficient? We can take, for example, the coefficient with P2 from here and with P2, P3 here, and this is only one way to do it, and we need to find this commutator, this guy with this. And I do it just with pictures. So I take this picture, so I will show you. I take this picture firstly, and then this, the last. Put it in this order, and this picture, and then this. And I have some factors here, and this P2, P3, they act on phi, so I put it here. And then what we use, for example, to obtain that this coefficient is 0, we use the unitarity property. So you can look that we have intersection here, intersection here, and just take this green line and it goes to the left, and we obtain this thing. It's just the unitarity property. And in this picture, we also use the unitarity property. We take these two intersection, and this line goes here, and we obtain the same pictures. And you may check that the coefficient, this coefficient, are also the same. So the coefficient P2 squared P3, it vanishes. And as in a scalar case, the non-trivial coefficient will be at P1, P2, P3. Okay. And there are more possibilities to do it. So, and we have 6 pictures here. And I draw these pictures, and they are matrices. So they are matrices, and this leads us to the first non-trivial R-matrix identity, which holds for Baxter-Belavin elliptic R-matrix. Okay. So this is the identity. We have 6 items, and you may see that some R matrices are shifted. The indices are shifted. Okay. I put down it here. So this example for first non-trivial identity, and again how to prove this identity. So it's the most simple, but the idea is the following. So you need to prove that the left-hand side doesn't depend on eta. And for this, you check the residue in each point, zeta I equals zeta j minus or plus eta, for example. And you use the following property for the Baxter-Belavin R-matrix, that the residue at the point zeta equals 0 is the permutation operator. And let me, for example, show you for it for zeta 3. This residue for zeta 3 equals zeta 1 plus eta. So we take the residue of the left-hand side of this equation, of these identities. What we need to do, we just take all our matrices with these indices 3, 1, and where we have zeta 3 minus zeta 1 minus eta. So we have only 2 items which give something to this residue. Okay, and I underline them by green color. So these are these items. And for example, we calculate this residue. So what we have R12 zeta 1 minus zeta 2, R13. And what we have here, zeta 3 is equal to zeta 1 minus theta, so, or plus eta, so we have minus theta here, R21, zeta 2 minus zeta 1 minus theta. It's for the first item, and for the second, we have R23 minus zeta 1 minus eta, R13 minus eta, the permutation, and R32 of zeta 1 minus zeta 2. And what we do next, we just take this permutation and move them to the right. What we have just here change of indices. So now we have 2, 3, and now we have here not 3, 2, but 1, 2, and this permutation we move to the right. And now you see the Young-Baxter equation. This minus this equals 0. So that's the way how we prove that the left-hand side has no poles. It's not so easy for general but you can do it by induction using the identities for smaller n, and you will obtain not just the Young-Baxter equation here when you move this permutation, but the identity for a smaller n. And you can do it by induction. And also you need to find and to check periodic properties of this R-matrix. Okay, this is some ideas for the proof. And now I'll give you precise notation and the construction of these spin operators. So we have this notation Ij with capital letters, but I haven't said, I didn't say you the order, yes. And here, what is the order? So we fix the order for the set J capital, such that J less than J2, so in increasing order. When you take all i's, which belongs to I capital, which less than I, in decreasing order, so this arrow means that this i's goes in decreasing order, and you take this product. So this is the precise notation. And this is the notation for R prime. Here is an example. N equals F, J is 2, 5, and I is 1, 3. So what we do, we have J in increasing order, we take 2, and all i's which are less than 2, it's only 1. So we put here R1, 2. When we take 5, and all i's which are less than 5, it's 1 and 3, and we start with in decreasing order. So we start with 3 and put here R3, 2, and then R1, 5. So thus we obtain this Rij. And for Rij prime, we take J, it's 2, and the indices which greater than 2, it's only 3, and we have R3, 2, and we don't have indices greater than 5 here and there, so it's only one item in this product. Okay. And what is the idea of the construction? So let me give you the important properties. So in scalar case, you may see that these Ruijsenaars operators are symmetric. What does it mean? It means that if you take some element of symmetric group, sigma, which acts as a permutation. So for example, the transposition sigma I plus 1 acts just permuting the variables zeta and zeta plus 1. And if you conjugate of any element of symmetric group, you obtain the same operator. And what does it mean? It means if you know the coefficient just before the first product of pi's, so I mean the first product in lexicographical order, so just you take P1, P2, Pk. So I denoted by I0 complement and I0. You can conjugate by all symmetric group, yes, by all elements and take this sum. So you just symmetrize this, and then you obtain this decay. So you need to know only the first coefficient. This thing before P1, P2, Pk. And what we do in the spin case? In spin case, we take another representation of symmetric group. So what representation? We take our R-matrix, some permutation operator, and sigma, which permutes the variables. Permutables is transposition. This permutation permutes the tensor I plus 1, and here the R-matrix. So this is the formula for transposition, but any element of symmetric group you can obtain as the product of transposition. So this is the representation of symmetric group. And why it satisfies the relation of the symmetric group? Because of Young-Baxter equation and because of the unitarity property. So you may prove that this Si plus 1 squared is equal to 1. Okay. And now we just base the representation start, which is the same as a scalar case and scalar Ruijsenaars operators. And when we act, we take the sum of all symmetric group. And I write it like here. So if you had transposition, you have any cycle you can write in terms of transposition, and any element which does the following: Im goes to M. It can be represented as the product of these cycles. So you just take this coefficient and then take the sum over symmetric group, and you obtain this Macdonald, this matrix version of Ruijsenaars operator. So this is the example. You have D1. You just put the same coefficient in a scalar case before P1. It's the following. When you you act by symmetric group, so by S1, 2, so you conjugate this to S1, 2. So what we obtain, if, for example, second item in this sum we have R12 bar, P12, sigma 12, by Z2 minus. And here the same. When we move, for example, these guys to the left and this to the right. Yes. And when we move this permutation through this R-matrix, we obtain R21, E1, and here R12. And when we move this to the left, it vanishes with this. And so what we have, so, and we need to change the indices here because we move this sigma to the right. So I change 2 and 1, and I change this one for 2. So we obtain the following coefficient. And here, yes, we have P2. So this is how the second item looks like, and you may check that it's the same as I have show you before, and the same with the second items. And so this is the way how to construct the spin operators. Okay, this is the summary of this part about spin, about anisotropic spin Ruijsenaars operators. So the main idea is that we construct some spin operators in terms of our matrix and prove their commutativity following by Ruijsenaars. So we find some elliptic, so some identities for this R-matrix and prove this elliptic Baxter-Belavin R-matrix satisfies them. So the natural question, which R-matrix you can use, for example. Yes, not only you can use elliptic Baxter R-matrix, yes, to obtain such commutative set of operators. You may use its degenerations like 6 vertex R-matrix, yes, rational R-matrix, 7 vertex R-matrix. So any degeneration of Baxter-Belavin R-matrix. Also, you may it works for SL for super case, SL NM case. So it also gives the commutative set of operators. But I don't know the good answer what R-matrices you may use for this construction. But there are some examples. Okay, and now I pass to the last part of my talk about long-range spin chains and how to obtain new integrable spin chains from these anisotropic Ruijsenaars elliptic spin operators. Okay, what is the idea? The idea is the following, that we have these spin operators and we use for them Polychronakos freezing trick. What does it mean? It means that we take this Hamiltonians in some special points. So not so they fix this zeta k in their equilibrium position. So zeta k equals k over n. It's the equilibrium position of classical Ruijsenaars model. And they fix these points. And we obtain some Hamiltonians. We don't have the coordinate space. Yes, we have only spin spaces, only vector space. And we obtain some spin chain. It's not obvious that it's so that in this way we obtain some integrable spin chain. So these Hamiltonians will commute. You need to prove this, why this Polychronakos freezing trick works. And this work in trigonometric case was done by Lammers-Pasquier-Serban and by Oglov, and they showed that in trigonometric case they obtain some Q-deformed Haldane-Shastra spin chain. So in general case, not general, not Q-deformed. So it's this chain. So this is the Hamiltonians. Here we have sine squared, and here are some numbers. So you can see that this difference of zeta, which are fixed in their equilibrium position. And here we have permutation operator. So in some sense, it's a long range degeneration along XXZ spin chain, because here we have the permutation in all components, not only for the neighbors, And if you take the trigonometric case of this spin Ruijsenaars operators, you obtain by the reason tricks the Q-deformed Haldane-Shastra spin chain. This is the first Hamiltonian. You can imagine that this R is just the trigonometric 6 vertex R-matrix. When you take the limit, it goes to 1, it goes to identity, and this middle thing gives you this permutation over sine squared and this sum over all pairs k and j in the limit. And in these papers by Lammers-Pasquier-Serban, they found this, they described the spectrum of this Haldane-Shastra spin chain, and they so it looks very similar to Haldane-Shastra spin chain, but it gives in terms of some Young diagrams. So you may see in this paper by Lammers-Pasquier-Serban about the spectrum and eigenvalues. So let me explain you in more details how this Polychronakos freezing trick works. So firstly, it was used for Calogero Sutherland models. So this spin chains of Haldane-Shastra type. This is the spin chain of Haldane-Shastra type is closely related with spin Calogero Sutherland model. And this relation is this Polychronakos freezing trick. So what we have? I have here some potential. It can be, as usual, elliptic, trigonometric, or rational. So in elliptic case, it's just P function, and this spin chain is known as an Anisotropic long-range spin chain. In trigonometric cases, 1 over sine squared, that is Haldane-Shastry long-range spin chain, and in rational, it's like this, and it's Polychronakos from spin chain. So, and the same potential we have in Calogera model, and if we take and if we use this Polychronakos freezing trick, we obtain this spin chain. So what is the recipe? The recipe is the following. You just move all these differential operators from Calogera and put all zetas in their equilibrium positions. So these equilibrium positions are the following for Calogera in elliptic and in trigonometric case, and in rational it's zeros of Hermitian polynomials. So you fix the points in equilibrium position of classical model of this model. So this is the recipe, and it works for Haldane-Shastry spin chain. And the integrability of this long-range Haldane-Shastry spin chain connected with the properties of Calogera model. And in trigonometric case, you may use many approaches for integrability. For example, approach from Dunkel-Cherenik operators to obtain the higher Hamiltonians. So you may see that it have Yangian symmetries, and also the Haldane-Shastry have Yangian symmetries. It's the work by Haldane and Bernard Gade Pasquier. So, but many works about this, how to obtain this freezing and how to construct the Yangian symmetry, or another approach to show the integrability is R-matrix Lux-pair approach for this Haldane-Shastry spin chain by Andrei Zotov. Okay, how to obtain the elliptic spin chain from our anisotropic spin Ruijsenaars-Macdonald operators? So the idea is the following. So you take this parameter, it's parameter eta, which we had in our shifts, and we just consider the expansion in this parameter of d, of dk. We take scalar operators, it's just scalar Ruijsenaars operators, and take spin operators. And the proposition is, if you take this difference, so you take the scalar Ruijsenaars operators, its first part minus its the first coefficient in expansion of spin operator, you take some matrix valued functions. You don't have here any differential operators. And when you take this H and you put the points in their equilibrium position of classical Ruijsenaars model, so you just put ZK K over N. And then we proved that these Hamiltonians commute. And this is the Hamiltonians of long-range spin chain. Maybe it looks very strange. Here I just want to show you the first two Hamiltonians for this spin chain. So R is our Baxter-Belavin R-matrix. F is derivative of this R-matrix. And we have such a sum here, and all points are fixed. All points are fixed and their equilibrium position. So this is the first Hamiltonian, and the second looks like this. And they commute. And also you can construct the next Hamiltonians of spin chain. Okay. And the last, what I'm going to show is that we can to show how the non-relativistic limit works for the spin chains. So what is not relativistic limit? Where this parameter h tends to 0. And if we have the expansion of our matrix, this parameter h, this Baxter-Belavin R-matrix, we have this first term, it's classical R-matrix. And it satisfies classical Young-Baxter equation. So this is the elliptic classical R-matrix. And if you take these Hamiltonians and take this non-relativistic limit, you obtain very simple H1. It's just the sum of derivative of classical R-matrix, and the second is it looks like this. So it's and these Hamiltonians commute. And for example, in trigonometric case, if this R is trigonometric and R small is classical trigonometric R-matrix, we have H1 in the following form. And this is the spin chain which was found by Hikami-Wadati in 1993, and then in this form, in this R-matrix form, it was found by Sech and Zotov, where they found and described the Lux pairs for Calogera system. Okay, that's all for today. I am happy to answer your questions.
Okay, thank you. Any questions or comments?
So these D operators look like Wilson loop operators as well. DK operator.
What operators? P?
Spin operator, DK.
D spin, yes.
It also looks like Wilson loop operators.
Okay. This? What?
Yes.
What do you mean?
Wilson loop operators.
Some loop?
Wilson loop.
I don't understand. I'm sorry.
Okay. Okay.
So what is the question? So
in other formulation, we can also construct these commuting operators by Wilson loop from consideration of Wilson loop. So they are commuting, and
they commute, yes,
yes.
for elliptic case, for six vertex case, yes. I don't know all the R matrices that you can use for it.
Right. So if you this Polychronakos freezing trick,
yes,
looks like modular these operators. So you have ground state, and you have these operators acting on the ground state, and then you have something left. So something's left looks like this Howden spin chain.
If you obtain this freezing trig. So you expand by this parameter of shift. So this pi, this p, they don't work. Yes. So
Right.
you have the expansion and then you freeze something. So you put the points in equilibrium position. So not all. So some items vanishes, of course. If you ask about the spectrum, I don't know about the spectrum in elliptic case, but for Haldane-Shastri and for Q Haldane-Shastri, it's well known.
Well, I think it can, yes.
For example, for Calogera, you know the spectrum, it's parameterized by Jack polynomials, and you can freeze them also and obtain the spectrum for Haldane-Shastri. And for Q Haldane-Shastri, you can use the Macdonald polynomials.
Yes.
Okay.
Okay, good. Yeah. So my question and comment is there is another realization. So coming from this fractional quantum Hall effect. So that gives a similar structure, same structure as well. Yeah.
Okay.
Yes.
Thank you.
Okay.
Okay, thank you for your question and comment. Anybody else? So if not, I would like to thank the speaker again. And our next talk will be also devoted to some long-range spin chains and connection with many body systems. And it will be Jules Lamer from France. Okay, thank you all for attention.